Hi, my name is Mark Dolnow, and today I would like to tell you about what quantization is and why we need it. In general, if you've ever been interested in the topic of large language models or LLMs or any other kind of neural networks, you've probably heard that right now. It's quite a typical situation when a model contains millions or even billions of parameters. And as you can see in this graph, that's indeed the case. If accordingly BERT took less than a billion parameters, then GPT-2 is already more, GPT-3, hundreds of billions of parameters. And basically there are models that are around 1 trillion parameters in size. Even the recently released DeepSeek, the largest size that is publicly available, that's 671 billion parameters. This is a lot of numbers, and we need to somehow launch the models well, not just in data centers, not only on big expensive servers, but also on simpler machines, including I would like to someday run them on home computers. So humanity has very quickly, it has come to the point where we need to try to save memory. And initially, you probably know that numbers in a computer are stored in binary. And in neural networks, probably the most common format is FP32. It's represented here as the second one. It takes up 32 bits, that's why it's called FP32. If accordingly you are doing scientific computing, you are more likely to encounter FP64, 6-set. It has higher precision, but it takes up 64 bits. So the first steps that people took were, let's try. We'll try formats like FP16 and BF16. They differ a bit in structure. BF16. It's more similar to FP32, as you can see from the number of bits in the exponent, but both FP16 and BF16 take up 16 bits. So in this way, we can already save money. Memory may only be half. That's a lot, but it's still not enough if we're talking about billions or even trillions of parameters. And so over time, we decided to move towards a more advanced, or on the contrary, simpler option. And here you can see the aforementioned in P32 and in P16 and BF16, as well as two common types. Right now, you know the world of LLM for quantized models, it's INT8 and INT8. If accordingly ours is in P32, if it takes up 32 bits, then INT8 only takes 8, which is 4 times less memory, and 4 takes up just half a byte, which is very little. Well, actually, that's not all. And there are even attempts at quantization now in 2 bits into 1 bit. And at the end, in this video, I'll tell you about how the aforementioned DeepSeek quantized into bits. Thank you. Well, accordingly, how do we do that? Here, we had 32 bits, and we need them. Fit into 8 or 4. How is this even possible? And here, a picture from the NVIDIA website will help us. It's very detailed. Let's pay attention to the left greener image. We can see that we have some distribution of our weights in the model. So they have some values. Some values occur more often, while others occur less frequently. Let's introduce 2 values. Here it's called respectively Amax and minus Amax. Let's take a value that is both greater than and less than. We're just going to trim it down. So as you can see, everything that is Amax or greater, we convert to 127. And everything that we have anything less than or equal to minus a max, we convert to minus 128. This is the first thing where we accordingly save. At the same time, we'll slice the other numbers into such little strips. We will naturally distribute the stripes more closely towards the center. That is, if we have such two subbulks are frequent, so we need more strips. Well, accordingly, we slice them into these strips. Well, accordingly, with you, we slice them into these strips, and we convert floating point numbers to the integer type, intit, which has only, if you look exactly 128 or 127, we end up with just 256 numbers, but we need a whole 64 to squeeze it into that. So accordingly, how it roughly looks, you can look at the right picture, also taken from the NVIDIA website. We turn the numbers dikputun into a more modest set. Naturally, this brings some problems. The model can just start spouting some nonsense. The model can get stuck in a loop. The model can just start working incorrectly. And we have to deal with all of this now. The approach of quantization-aware training is very common. This is when, already at the training stage, the models kind of simulate what it will be like. Then it gets quantized and happens. Such training, when the model kind of knows that quantization awaits it in the future, and it works quite well. Nevertheless, this way even with some difficulties, we can save in memory and reduce the required amount. So let's think about how we're going to store this. What data format will work for us? There are actually a lot of them. They diverge. But right now, one of the most common is GGUF. This is a format developed by the person behind LLMs, and it has several advantages. But first, let's get familiar with what this file looks like. So we have the magic number GUF at the beginning of the file, taking up 4 bytes. Next comes the version, and at the moment it's already the third one. After which, accordingly, we go the number of dances. Information about how many key value pairs will we have in the metadata. The metadata follows information about the tenses, and at the end there's an offset. So this is what our file looks like and what advantages it has. The first advantage, which is very important, in fact, this means that we will have one file for everything. So in GGUF, we record all the information needed for the model. This includes both the weights and the aforementioned metadata. And information for the tokenizer, which will turn our letters into numbers that our model will process, and vice versa, numbers into letters that we can understand. And all of this fits into one file, which is very convenient for distribution. You don't have to give there some kind of archive with 20 different files, each of which has to be named correctly. You have one file for everything. And the second thing is memory mapping. This a trick that allows us to directly, as it were, compare our RAM and a file on the hard drive. So we can load directly. This allows us to load models very quickly. And we don't need to read the entire file at once. Well, for example, thanks to this, we can, in particular, load a piece of the model, work with it, and then load it back. And this happens very quickly. We have no requirement for reading the file, waiting for it to be fully read. We can do this in chunks and immediately load it into RAM. It has, compared to other formats, it allows for convenient storage of metadata. You can write down what type of architecture our model has. You can write down some details about quantization, hyperparameters. There you go. Very useful information. It's quite easy and straightforward to store, as we saw on the previous slide. And it supports quantization out of the box. So in a sense, when it was being developed, quantization was already on the mind. Thanks to which we have the same int8 and int8. It holds it without any problems. And as we move forward, Gypsy in quantized bit, also in GGUF. There are a lot of different types of quantization that are supported. They are all available, for example, on the Hugging Face website. And accordingly, let's talk a little bit about the much discussed DIP6, or a large language model from a Chinese company. And it turns out that their largest model contains 671 billion parameters. That's a very, very large number. And in the original, the file weighs 720 gigabytes. That's a lot. But just recently, at the end of January, well, the team at Unslapped AI quantized this model into bit, thus turning 720 gigabytes into 131. Here, I'm lying, because in reality, they didn't quantize all the weights. They quantized some of the weights less aggressively, less strongly, because if we quantize all the weights, all the layers, then, according to their experiments, the model either got stuck in a loop, meaning it would just output out 2 to 3 different words and then keep repeating them constantly, or model just lost the ability to provide any meaningful responses. You might be intrigued by how it turns out bit. Well, if we're being very rough, we use 3 numbers, -1, 0, and 1. So, if you take the base 2 logarithm, might of the number 3. So accordingly, here we have this Frankenstein that was created, which has been quantized in different ways, is stored in a very unclear manner. In GGUF, there are different weights with different quantizations. It's probably hard to work with it. Actually, no, according to the authors. And basically, I checked, it's pretty easy to run. You need at least 20 GB of RAM to run it. If you want to run inference on a CPU, it will be very slow, but at least it will work somehow. And 20 GB of RAM isn't that much. Unfortunately, you'll also need a hard drive with at least 131 GB of free space. And if you're going to install this with browser wrappers, something like that, then a little bit more space. But still, you need just a little bit of RAM. You can run it on a single RTX 4090 graphics card, for example. The RTX 4090 has 24 gigabytes of its own RAM. And there, according to the benchmarks, it comes out to about 2 to 3 tokens per second. It's not much, but it's enough quickly so that you can at least somewhat communicate with the model. You can fit it entirely into 2 data center H100 graphics cards. Such a model in 2 data center H100 graphics cards and get if you launch one user, then 13 to 14 tokens per second somewhere. And if you launch more users, then there are a lot of people are interacting with the model at the same time. So the maximum speed is about 140 tokens per second. And it seems like that's even more than is now available in the DeepSeek API. And here's the ideal setup for running this model on your home computer. The condition is that the amount of your RAM is processor regular RAM, and RAM is video memory, which is the memory on your graphics card. And if their total is greater than or equal to 80 gigabytes, then overall the model feels quite snappy. Well, in conclusion, we can take a look at the comparison. Actually, the team which quantized conducted an interesting experiment. They asked the model to write a Flappy Bird game, and in the end they judged by whether the code runs are different shapes used instead of the bird. So we see a little circle, a triangle, counting points it runs, and overall the code even executed. So this is also a kind of necessary conditions. And here are two GIFs. What do you think, which one of them, the model that was quantized to bits, which one of them is the model that wasn't touched, the original 720 gigabytes? If you accordingly, you can look closely at different details and so on, but this is a game that was written. It's hard to say right away that one of them is significantly worse than the other. Actually, on the left, the game is written with the original uncompressed model, and on the right, it's written with the quantized one, already quantized. Nevertheless, the results are very impressive. And basically, if you're really curious, as I said before, if you have 20 gigs of RAM, you can try to run, you have it with you. That's all from me. I wish you good luck and pleasant discoveries in the world of LLMs and beyond.